welcome everyone to our second meeting. We have a bunch of important topics to discuss, and there'll be three parts to it. So one will be physics-like questions about unification and dualities, so something that we'll try to understand from the point of view of the neural network theory. The second kind of questions will be evolution as learning. So that will be a continuation and discussion we had previous week. How is it that the evolution can be viewed and described through the learning dynamics? And the third one is more philosophical. So here we'll be not knowing what we are talking about, but we'll still try to do that. We'll discuss possible philosophical implication. We'll begin the discussion of the possible philosophical implications of whatever we are, whatever the theory tells us. So let's start with the first one, and with the first question. The question is how can we unify the four fundamental forces of nature? And the follow-up question to that: how do quantum mechanics and general relativity reconcile with each other? So I understand again that not everybody is a physicist here, so let me just tell you what those words mean. Basically, there are our best understanding of physics right now that there are four forces: electromagnetic force, weak force, strong force, and a gravitational force. And physicists were able to unify the first three together, and they're kind of of the type that they were of a similar type. There were similar techniques were used to develop them. And then there was this gravitational force, which is different. So for the first three forces, there is a space which is flat, and on that space there are particles that are called fermions, and they interact with each other with forces that are mediated by particles that are called bosons. And so that was kind of the rule how we describe them. And then there came gravity, where now the space is no longer flat. It acquires its own degrees of freedom. It starts to breathe and stuff. And so that was basically the problem of unification. And when people say reconciling quantum mechanics and gravity, it's basically taking those first three forces and trying to reconcile with the gravitational force. How can you do that together? And now, if you recall from last time, so there are many details we can discuss about how this unification would work exactly, and we'll have many meetings about that. But the basic difference between that was highlighted last time between the regular physics, the classical or quantum, and the neural physics that it proposed is that there is this new type of dynamics, the learning dynamics. And without this learning dynamics, everything behaves as normal physics, as activation dynamics, as those first three forces. And it is only with this new type of dynamics something weird or something different happens. And so the way that those two types of forces are unified in the neural network theory is that you view that there is one type of dynamics where things are mostly not learning or already learned everything they could, and that corresponds to the weak, strong electromagnetic force. And then there's this other force, which comes from an actual mostly learning dynamics. The also macroscopic difference between the two types of dynamics is one that leads to entropy production. And if you start with a bunch of molecules of a gas in a corner, they spread out through the entire room, entropy grows. But for learning, the opposite happens. And we see that in a gravitational system, the opposite happens, right? You start with lots of stars floating around, but they try to collapse. There is a gravitational collapse that pulls them together, tries to decrease the entropy, which is similar to what the learning system would do. There's many more details, so this is just a rough idea of telling you why those two things are different. And the neural network theory, you're just telling you they are different is because they're different phenomena that dominate to describe one force and to describe the other forces. Okay, so are there any thoughts about it, any ideas or whatever comes to mind, or questions, anything at all? We'll be talking about the unification a lot later. But that's kind of this was one aspect that people had been struggling with for many years in physics.
There is one question that comes to my mind.
Go ahead.
Is that, so you mentioned that there is how to say, a basic physics that is regulated by the laws that we more or less understand. And there is the learning part, which works on top of that. Now, are you talking of something like what philosophers call supervenience, which means that, there is something new, but that something new essentially works without overriding what it works on, or is some entirely new?
Well, it's a new ingredient
that
right?
We still don't understand.
Yeah. So as a mathematics of it, right? So there is a new ingredient, the learning ingredient. So we didn't have it before, now we have it. And now we can play around and say, okay, do we need it? Can we describe everything without it? Or do we actually need it?
But
and that
would you call it strong emergence or weak emergence?
Yeah, so we did talk about emergence before, and we will talk about more. Now, everything in this theory is kind of, all the macroscopic things so you see, all the forces, they do emerge from the underlying theory of the neural networks. Everything that, well, everything that we are used to be calling fundamental, things like, fields, like electrons, particles, all this is an emergent phenomena from the underlying dynamics of the microscopic neural network in this picture, right? What is different, however, is that we are extending the mathematical apparatus of writing down those theories. So before it was classical and quantum, now there is a new type of mathematics that governs the dynamics. And this new type of mathematics is the learning dynamics. There's something that wasn't there before, we added. It makes life a lot harder. Modeling dynamics of such things is harder. Now, before you would write down something like Lagrangian and Hamiltonian, and you know how to solve it. Now you have to write a loss function, and then you solve it. So, but that's the idea.
So it's not simply something that is emergent from the laws of physics that we more or less understand. It's something entirely new.
That other way around. So what is more fundamental? In this picture, it's other way around. The underlying mathematics is the neural network dynamics. From that, you have the emergence of fields. Now, from those fields, you have emergence of later on you have emergence of biology, and there they have their own neurons, which are biological neurons, but that all comes later. Underneath of all that, there is learning dynamics. Yeah. Okay. So I'm going to switch to the second question because that may take you from in a more comfort zone from the uncomfortable zone of physics. So now we are moving to saying, well, okay, so let's say you unified quantum mechanics and general relativity, but can this framework be actually used to unify other fields, right? So bringing together physics, biology, and psychology, philosophy, everything. And that's kind of the big program of actually all those meetings. We're trying to check that. I don't know the answer. There might be some phenomena in one of those branches that they're just impossible to see being emerged from the learning dynamics, and then that will be interesting. Then we'll have to think about how we can generalize it, or maybe choose some other framework. But that's the idea. Can that be done? Can you take the neural network theory and potentially unify everything? And that's a very, very difficult question because, biology is complex, psychology is even more complex. And the higher level you go, there are more and more complex phenomena take place. And however, the idea is that maybe similar phenomena will just keep reappearing on every scale in this hierarchy. And if that's so, we can learn from each level. So we learn something on the level of physics, and that tells us something about biological level, and tells you something about psychological level, and vice versa. And then in a way, by unifying, you're not only unifying, you are helping to fill the gaps of knowledge in each of those disciplines. This is the big program. This is the program that kind of why we are all meeting here. or people with very, very different backgrounds and very, very different, set toolboxes, right? I don't know if it will fly. I don't know if it will work, but that's the hope. Any other thoughts on that?
To me, it just seems like a great place to look if you're looking for answers. Because hi, I'm Josh, everybody, and I'll just get two quick points that I think really nail this home for me. We know from experience that you can get extremely complex life forms from very basic cells, like that can do very basic things. We could, at this so basic, we could just, say neurons, cells, whatever. There's very, very basic biological things can give you this almost infinite panorama of complexity that we see in the world around us today. And so if the math, if the math between that and what we call like classical physics has some sort of correlations or dualities like we're finding, then it would kind of make sense to kind of come over here and look at classical physics and be like, oh, quantum physics, and look at these both and be like, could they also arise from very simple cellular or neurons in a similar way? Could that be how we arrive at sort of this very complex universe that we observe today? I think the question makes perfect sense, and I think scientists and philosophers have always been like, there's these weird similarities between the two, but until the math started coming together, we didn't really know what it was. And so what I really like about what VV's doing is he brings the math to the table and shows a lot of similarities between the two. And the question, like he says, is still out, whether that is just a similarity or it's just a math trick, or is that really the fundamental thing? And I personally believe we're getting down to the fundamental levels, but there's still a lot of work to do.
Thanks, Josh. Yeah, that's a good point. We just want to go beyond analogies, right? So analogies are great for when you learn stuff like, look, this looks similar as the energy conservation. This looks similar as momentum conservation, or whatever. We want to go beyond a lot of analogies and start making prediction on all those levels. We're trying to take the math, which seems to work pretty well on a physical level or machine learning level. Now we can bring it to other disciplines. That's a good point. Other comments?
Hi, Vitaly. I have one question. About probability and infinity. Neural networks and their relation to probability and infinity. It's a question for me. I don't know how it's relate each other.
Right. Well, okay, it's off the topic, but for now, for the I'll still answer, right? So for the analysis that we do in artificial neural network, we make an assumption that neural network is finite. So we take finite because that allows us to do calculations. Now we can take limits of network being bigger and bigger, and then obtain those results. But probability are everywhere there. This is like it's all science is probability theory. You just can equate science equals probability theory because nothing is exact, and you just have to make best predictions you can from the informed predictions, right? From the knowledge that you have about the system. And so all science should be like that, whether it's biological, psychological, or any other phenomenon that they're trying to study. There is some probability theory that some calculations within the context of probability theory that you need to do. What is often hard is to identify what are the right calculations, and that's that's the separate topic, and we'll go into that. But that's certainly.
Neural network is a Turing machine, so it's deterministic, as I understand. No,
you can have a stochastic gradient descent method when it's not deterministic, and it will be stochastic. We will definitely talk about this, but not within the unification and duality chapter of our discussions. I actually would like to bring us closer to the dualities because that's something people probably don't know much about, and that is kind of been a big thing in physics recently. And I'd like to really tell you what it is. So with this understanding of the duality, you kind of can appreciate of what is being done, or other way around, trying to question whether this is the right way to do things. And that came from the research in the string theory, and we'll put string theory aside. but nevertheless, although it does have connection to the neural physics, but we'll just need to dig deeper into the mathematics of that. But let's take this one idea that came from a string theory and proved to work very well. It's called the holographic duality. Now, holographic duality is only one example of duality, but illustrates very well the point that I will try to make. Now, what is a holographic duality? Holographic duality is when you have a theory that has you can write it one way by writing as a certain integral or partition function in the bulk, and then you have another way of writing the very same theory, but using integration or partition function on the boundary. So basically, the two mathematical ways to write the very same theory. Now, once you wrote them, those two separate ways, you can look at it and say, okay, which one is the right one? Which one, how does the universe work? Does it work as the bulk view of the theory or as a boundary? The answer is, it's a relevant question, because from the point of view of doing actual calculations, you can use either. And if science is all about making predictions to whatever experiments you're about to do, then there is no difference. Now, philosophically, you can, of course, look at it and say which is like the primary view in this duality, and then which one is the secondary view, which is just a convenient way of doing calculations. But from the physicist perspective, they're like two sides of the same coin, two views on the very same theory. And if the duality is exact, then there is no way of us telling which one is more fundamental. Now, so that's a general view of the duality. What is interesting in the holographic duality is the bulk and boundary. So we always thought that kind of degrees of freedom live in the bulk. So you can like take your configuration of particles, specify their position in momenta, and then after that, write down equations of motion and solve how they would evolve forward in time. Well, it turns out that you do not need to do that, and there is too many degrees of freedom in the bulk. Really, you have to specify less information to describe your system. You do not need to specify three-dimensional information. You can specify only two-dimensional information. So there's fewer variables that needs to describe your system. Now, so there are like two new ideas here that I think you should try to appreciate. One is the duality of how you do calculations. You know, if you do have two theories that kind of, or two approaches to calculations that just give you identical result, you know, you don't know which one is more fundamental. And the second one is bulk versus boundary. It is interesting that we do think that, you know, there is kind of a bulk degrees of freedom everywhere, and I'm able to change configuration of one particle in my hypothetical sphere, and that would correspond to a new state. But the holographic duality is saying no, you cannot do that. Questions about that before I go on and tell you what's the neural network take on that?
I guess you're going to come to that, but I was wondering, in your framework, what is the bulk and what is the boundary?
Right, we'll definitely come to this once I describe the neural network take on that. But or I should just jump into that. I'll wait a few more seconds to see if there are any questions about the setup. It's very new. It's actually it is only in the 90s that Moderator proposed that it is wrong for us to quantize gravity as any other theory which, you know, lives in the bulk, has like three-dimensional degrees of freedom, and somehow you have to map it to a lower dimensional theory which lives in the boundary. So let me just give you a simple analogy of why this duality makes sense in the context of learning. So consider a neural network and think about this as any learning system. Consider it as a bulk And then it is trying to learn its boundary. So it's trying to adjust its weights so that it predicts better how the boundary behaves. Well, it is only learning the boundary, right? It is not learning the bulk, it's learning the boundaries. All it needs to do is to adjust its degrees of freedom such that there is enough information in those configurations in the bulk to predict how their boundary evolves. So think about boundary as environment and bulk as the organism, like coming to the biological context. So it's only the boundary that the organism needs to learn, because that is where it is interacting with the environment. So it is fewer information that needs to learn. A lot more can be, a lot more information in the bulk can be redundant, shared. Now, the other example we discussed last time, if you remember, when this transition, biological transition took place, original life biological transition, what happened is that the separate organisms started sharing degree of freedom. They started share the degree of freedom, their DNA, and those degree of freedom they tried to start to train. So once again, they're reducing the independence. And this reduction of independence is in agreement with having less and less information in the bulk, because that's what all you need to actually model the bound. So that agrees very well with the idea of holographic duality. Although exactly by how much you want to reduce and what are exactly mapping, and is it true that the system is learning its environment in the context of gravitational physics, there are a lot more calculation that needs to be done. But yeah, that's the idea. Other questions, ideas?
Vitaly, what about Hilbert space and your neural physics? How neural physics
Right.
can explain Hilbert space?
Yeah, so that's question of quantum mechanics. We'll get there. So it's not one of the topics here, but it is the quantum mechanics is emergent concept here as well. So you do not have Hilbert space on the fundamental level. So we will discuss it, I promise, Alec, but not now. Okay, so
one thing, Vitaly, since you are assuming that there is a holographic-like duality.
No.
So doesn't learning the boundary or learning the bulk means exactly the same thing?
Yeah. So holographic duality is not assumed anywhere. Holographic duality in string theory is a conjecture that it allows them to do calculation. In neural physics, there is no assumption of holographic duality. I'm just explaining why such a thing makes sense. Why would the holographic type duality? Later, I will talk about different duality, which I think is more important in neural physics. But I'm just explaining why it makes sense that the bulk has fewer degrees of freedom that you would naively count. So it's not a volume-like degrees of freedom, but a surface-like degrees of freedom. It is only makes sense if this bulk is trying to learn the boundary, and that's it. So like you have an organism who is just trying to predict the environment. It doesn't care about its internal structure. Not necessarily the case for more advanced organism, but from the view of the learning theory, sharing the degrees of freedom, which is not needed in usual physics, in neural physics, it does make sense. Also note the other thing I've mentioned, that in the learning dynamics tries to reduce the entropy, right? So reduction of entropy is also equivalent, saying you are not really exploring all of the phase space, but you are exploring a lower dimensionality space. You are copying information, the same information in many different places. So that's the idea. Other questions?
So may I name neural physics is a physics of entropy reduction? Is it?
Well, it has that component, right? So what's new? Again, I mean, this neural physics comes with very different realizations and very different limits. But one is the learning dynamics, and the learning dynamics is the one that violates the second law badly, and it creates the second law of learning. You're trying to reduce the entropy, and not the other way around. And that's kind of important aspect of that. So let me just throw this one more duality into the picture, because I think that's kind of more related to kind of understanding how the neural physics works. So is there duality between classical or quantum usual physics and neural physics? And it seems to be there is. So there's now this two languages of writing down a theory. You can write down a theory saying, okay, there is my Lagrangian, my Hamiltonian, or energy, or you can write down and say, here's my loss function. Okay, so there are two completely different ways of saying what the theory is. So in one case, you have well-defined rules of how to write down classical equations of motions, how things evolve. And the other way, you also have well-defined rules how to write down loss function. And then the question is it a duality? So is it true that for any system which evolves according to classical quantum equations of motion, I can write down a loss function, and then similar behavior will emerge from the learning dynamics? And so the one example where we show that that's possible is in this autonomous particles paper. Basically, what you start is you can think about electrons as electrons that are fermions, and they move in the electromagnetic field, and they according to some Lorentz force or whatever. Or you can think about those electrons as autonomous vehicles that are trying to navigate the three-dimensional space. They have some learning objective of what they want to do. And then according to this learning objective, they adjust their strategy of moving through the space. And then they adjust their strategy. But at the end, in one picture, electrons are moving, and in the other picture, electrons are moving. Now, and if we want to have a total map, duality map, then we say, all right, in one case, tell us what the Lagrangian is, and we know that, Hamiltonian Lagrangian for electromagnetic theory. In the other case, tell us what the loss function is, and then the mapping is completed. So if we can come up with a loss function that does exactly what electrons do in that other picture, then you have this dual description. And the question of which one is correct is irrelevant if they have a one-to-one mapping, if they are just give exact predictions. However, usually the duality is not exact, and so you should be able to observe deviations from the in between the two pictures, and that's where the fun begins, right? So now you've come up with a different mathematical framework of describing the dynamics of electrons, yet it is a bit different. And then I say, all right, let's test it where it's a bit different. Is it? And that's kind of the interesting part of it. But the duality is exactly between the normal classical quantum physics and the neural learning setup. Okay. Okay, so now I want to phrase this more, maybe philosophic question. Now, duality. So we have like two mathematical frameworks, and let's assume they're exact, and they describe exactly the same phenomena or set of phenomena, maybe all phenomena. But they're different mathematical tools, right? They're different mathematical frameworks. Should we say that this duality is fundamentally there, or should we say it just happened? And is it important that there is this two dual views, or should we say it is just something that emerged from our consideration? So is there more to this? Should we actually be thinking that duality should have been there on the first place, or maybe something that coincidental? I don't know the answer to that question. So we have examples where duality seems to be exact. It's like two different ways of writing the very same thing. And yet we cannot claim that there's some fundamental reason for the existence of those dualities. Maybe this is just our inability to really understand the true nature of the system makes us use whatever mathematics we have to model that, and then we use whatever we have, and so we have many different things that we've discovered in mathematics, and so one of them worked, and the other one worked even better. So I don't know the answer to that question. So I don't, and that's maybe more philosophical. I don't even know the answer to the question is, does it make sense to ask, demand that one of the dual pictures is more real than the other? Should be like, we will always try to say, oh, it's just mathematics. There is real physics behind it, right? And in this case, it shows that, well, there are actually those true mathematics that, and we don't even know which one is more fundamental. I don't even know if there is any sense in which we can claim that one is more fundamental than the other, or if it makes sense to actually make such claims. So I don't know what you guys think about it.
I agree. It doesn't make sense to think about which one's more fundamental yet. They both, I don't know more to, I can't say much more about it than that, but they seem to be on equal footing.
Right. Yeah. And eventually, the one may win, right? So you may get some phenomena that is described from one view, but not from the other, and then that would be, of course, interesting to see if that happens. So certainly, with the classical and quantum physics, we were not quite able to describe, general relativity, within the same framework of classical and quantum physics, especially quantum physics. So there was a problem with that. But with the neural physics, there isn't such an issue, and so maybe that makes it better. Now, also there's entropy problem with the standard physics, where entropy must grow, and then, in such a universe, I wouldn't expect observers like us to emerge, because we are very complex and yet very low entropically very low creatures, and so then. Other comments on that?
Just thinking it out, no? I think very generally and very philosophically, I don't see an absolute need to unify everything, in the sense that we have some laws for one part of nature and some other laws for some other parts of nature. Mm-hmm. As long as these two sets of laws work together without inconsistencies, then that's good enough for me. Maybe the two can be derived from the same more fundamental layers, or maybe not. But I would suggest of not letting the quest for unified aesthetics prevent us from finding out how these things work. Two different sets of law, I believe, is good enough at this moment.
Yeah. So thanks for the comment. The problem is not that we're like unification of the physics. That's not the problem, right? The reason we seek unification is because there are known limits when we don't know which one is applicable. So it's not because we're like beautiful unified theory, right? It's just because there are limits where you just do not know which calculations you should do, and that then you cannot make predictions about how the system will behave. So black hole physics is one example where many such phenomena emerge, and that is why we are seeking for unification, trying to see, well, if there was one underlying principle that will just tell us there is one unifying framework, and there are just different limits to this framework. This is a limit where general relativity calculations make more sense. Here's a limit where quantum mechanical calculations make more sense. And that's kind of what neural physics tries to do, right? So you have this one unified framework, but then you have to search for all those limits. And again, we can go to the biology and psychology. It's yet other limits of the dynamics. And so the unification is not so much about us liking it to look pretty and stuff, but to be able to know exactly what calculation to do when, exactly when, or which predictions to do when. So that's unification. Duality is different. Now you can have two perfectly consistent frameworks, theories, but they are written in a completely different way. So as I said, like one in the bulk, one in the boundary. Are we two-dimensional creatures that just hallucinating to be three-dimensional because there isn't enough degrees of freedom of view, or not? And that's kind of the questions that will come, philosophical questions that will come with duality. If you have those two mathematical frameworks of describing the very same system, which one is more fundamental? But anyways, so let's move on. We are now we're done with physics, the complicated stuff, or the simplest stuff. Of course, now we're moving to more complicated stuff, but at least there everybody will have an opinion, right? Once we come to philosophy, then everybody's gonna have an opinion, right? So that's what makes it fun. Okay, so I wanted to start with one of the questions that we kind of touched last time, and we didn't have enough time to discuss, and that I think it's very important. So let's say yes, there's a learning dynamics that governs evolution of the universe on all scales, biological or not. Maybe let's talk about biological scales now. But then there is, and then we're trying to understand, well, how do the organism evolve? What is their objective? Yes, we want to identify the loss function, but maybe loss function is really microscopic and it's a hard job. Maybe physicists will do that with this duality mapping we discussed. But let's move on to biology. And then what is the objective of organism? And then there seems to be two proposals here. So one, it was the old one saying that, well, the survival, the objective is to survive. And then whatever you do is to survive. And then the other proposal that comes from this paradigm is learning. So, and then the question is, do you learn in order to survive, or do you survive in order to learn? Certainly two come together, because if you didn't survive, you wouldn't be able to learn. But also, if you didn't learn, you wouldn't be able to survive. And so now it's becomes a bit, we're going to loops here, trying to understand, well, what would be more fundamental? What is the objective, right, of organisms, I don't want to say the meaning of life, but we could also push it that way. And at some point, I will raise this question, more philosophical question. But what do you think? Do you think survival is just a byproduct of us being able to learn, or learning is as a byproduct of our desire to survive? I don't know. I don't have the right answer to this question, but maybe somebody has.
I wanted to clarify, simply saying, I think by learning you mean changing, evolving.
Well, no. By
or
learning,
directional change.
No, I actually mean learning. So you are learning the environment. No, not necessarily. There are many things change, right? So the state of the physical system undergoes constant change. But here it is learning. What
do you mean by learning? Define learning, please.
Yeah. So it's trying to minimize the loss function. And in this case, maybe the loss function is the ability, let's say, like for the sake of the argument, ability to predict the environment, learning more about the environment, right? So you have an organism that tries to learn the environment. The more it learns the environment, the better it's able to predict how the environment will behave, the more likely it will survive. So when a kid is just born, he doesn't know that the danger is everywhere. He can roll off the bed and hit his head, right? Eventually, he learns that that was not a good idea, and then, or when the rock flies your way, you don't necessarily try to grab it and it hits you. But then you learn that was not a good idea. And so next time I see a rock flying your way, I'll just try to grab it or move it to the side. So you are learning how the environment behaves. That allows you to survive, for sure. Okay. But which one is primary?
Can I ask one question? Reaction or proaction? Because when you learn, you know how the environment, what environment is. But then our next step is to change this environment.
Well, that's
we don't wait for the environment to change.
Right.
We change the environment ourselves.
Yeah. Okay, Alex, very good. But you are adding more terms into the loss function. I'm trying to make it as simple as possible. So it is true that I can actually adjust my state, move to some place where I would be safe. And that would be my way of avoiding the danger, right? But I want to make things real, and then that would be another term, like in the biological paper, we say just another term in the loss function. One term is kinetic term. I call it a kinetic term. Ability to predict the environment. When something suddenly changes, I know exactly what will be and what will come next, and so I know how to avoid it. But then the second one is potential. I'm trying to go to the environment when there is more food, when it's a safer place, and they're just different terms. Both of them are learning. Trying to optimize. But again, I mean, do I learn it just because I want to survive? Okay, or do I survive because I want to learn? And it seems to be like somewhat. Again, I mean, this is an open question. I don't have a precise answer to that. It seems as if the learning theory suggests that the learning is more fundamental, and the only reason you survive is just because you have the loss function to minimize and learn. But I don't know. I mean, because the reason I say right now I don't know, because I am not making this discussion on the fundamental level. On the lowest level, yeah, it's all learning, it's all loss function. But I've moved a layer up to a biological layer, and whatever is, and there's no guarantee that at that layer, one or the other would be more important, and so it may be just a philosophical question, but interesting nevertheless.
I think I have some problem with this concept of survival. Within the theory of learning or evolution is learning, I understand that it is about learning, but what is survival? I feel that now the order in which we discuss the topics may be not perfect for my understanding, because to discuss survival, we need to discuss the concept of self, maybe. Who survives? What is this concept?
Well, let's say ChatGPT. We don't need to have a self, right? Some ChatGPT or this some AI robot. That was said, learn something, okay, and then to optimize that, to learn something, the robot would want to survive, because if he doesn't survive, then he wouldn't be able to accomplish the learning task. And so we know here that the reason why he survived was learning, because he was instructed to learn. The robot, and there is no self there. There's just the robot. Well, I mean, no offense to robots, but and then the primary thing would be learning, and survival would be just byproduct. Like you cannot learn without survival. But you can imagine other way around. Then you just want to survive, and the only way to survive is to learn the environment, how it behaves. Right? Because if you don't know how the environment behaves, you wouldn't be able to survive. So then what's your objective? Is your objective to learn as much as you can, or just survive?
I think in biology, the main task of species is learning, and main task of individual is survive. It's different aspects of the self and individual survival, and the learning is a task of the species.
Yeah, well, that disagrees with what we are trying to say. We are saying that when you move from species to group of species, anywhere, on any level, it is just the very same dynamics. We call it different things, but it's, there is a level of atoms, there is a level of cells, there is a level of multicellular organisms, there's a level of groups of organisms, and all levels the same thing happens. This scale, this organism, on each of those scales, trying to do something, and it certainly learns. It certainly learns its environment, right? Because it's not only that cells learn their environment; multicellular organisms together learn the environment by collaborating with each other, right? So you will be measuring temperature, I'll be receiving like light signals, you'll be doing this, I'm doing that. Everybody assign role, and now this whole organism with multiple cells is able to learn. So definitely learning takes place. Now, and definitely learning helps the organism to survive, because the more it learns, the better it survives. But what is the goal, right? And that's the question. Yeah.
Just one little thing just one little thing. Well, if we travel a little bit more, like a little bit more, so we can find out that, let's say, 5 billion out of 8 billion, they just surviving,
Right.
they just surviving. Just we should take Katya, and make her travel a little bit.
Right.
So because
well, everybody's gonna go on a trip, right? Road trip.
Well, actually, it's impossible to express his words.
Right.
You have to express.
It's very well that you stated this. Sorry, I interrupted you.
No. Please, let me finish.
Yes.
So then, what you can do? You can actually travel inside of your body. And when you travel inside of your body, you look at these little cells, and you know what they're doing? They're fucking surviving. You see? So travel a little bit. And we'll make you travel to the world and to your body.
Yeah. Okay. So they're surviving, but they're surviving by learning.
Of course, like that.
What's the most fundamental one?
Yeah.
Okay. I think we'll not gonna resolve this. But that's the point, right? So I would prefer to say that
no. Yes, we will resolve it, but it will be not like you think. We'll destroy this question, but not now. We'll destroy this question, but not now.
Sure. All right, sounds good. Okay, just remember that's an important question to ask, and maybe it just doesn't. Maybe we just should put a equal sign, right? And then that would be another duality, right? So the duality of objective being learning and duality of objective being surviving, and then both of them seem to be correctly describe the behavior of organism on that scale. I don't know, but that's something to discuss, to talk about. Go ahead.
One idea I had, how we talk about at the beginning of the universe, potentially the forces were unified into one, right? So, it seems like at the beginning of organisms, learning and survival are like this unified thing. And as the organism becomes more complex, you can maybe determine a difference between the two, survival versus learning. But when you do a thought experiment on the very first organism, survival is like this probabilistic or stochastic thing that it has no control over. Next iteration, it exists or it doesn't, but it has no ability to do anything yet. And learning is moving that needle so it's not 50-50, or now have a 51% chance of surviving the next iteration. But at that first organism, they seem like that first instance, whatever that is, we don't know. They seem very similar. They seem unified, but as complexity increases, they seem to diverge.
Okay, so I'll add, thanks, Josh. I'll add a little bit to that. So actually, as the evolution progresses and there are more and more clever learning algorithms are discovered, there is one algorithm that discovered that goes against survival, and that's called program death. So organisms evolve, they discover new ways of collaborating, and there's new levels in this hierarchy are formed. And then all of a sudden, some substructure of those higher structures figure out that it is better to die than to live further, and then they just kill themselves. So it's a program death, and that seems to be essential for this global task of learning. And so, with this respect, the answer would be yes. Learning is more fundamental, and survival sometimes it's beneficial because you learn, but other times just not important. And so that's and as Josh said, this is something that you may not have in the beginning, but eventually, as more and more phase transition the evolving system undergone, and more clever learning algorithm discovered, it figured out, well, survival is just you don't put too much meaning into that. It is the total learning objective that needs to be optimized. All right, so let's move on to the next question. We spent a lot of time on this.
Hold on. I'd like to say something because I have to jump out in 5 minutes or so. But this is a good point. Now, standard evolutionary logic would have that survival always comes first, and learning makes sense if it has evolutionary value, being useful to survival, but otherwise is a byproduct. So from this point of view, which is not mine, it would seem that survival has to come first.
That's
now,
right, exactly. That's exactly the point. That's exactly
the example of the programmed death that you made is very interesting in this respect, because it shows that sometimes the best thing in some larger context, the best thing for the group, the best thing for the species, is for the individual not to survive.
That's right.
This seems to put some problems on the standard evolutionary logic. Now, just one thing I want to say quickly, and maybe we discuss it another time. We have left the part of the discussion about fundamental physics, but it seems to me that this is very much related to the nature of time. If there is an error of time, which the present becoming the future and that becoming the future again, and so on, that it seems difficult to deny the validity of standard evolutionary logic, according to which survival comes first. But if, I'm thinking aloud, if we allow for the possibility of a more complex nature of time, something with, feedback loops across time, closed time-like curves, these kind of things which seem to allow for the future to have some kind of causal effect on the past, as in retrocausality, then I think the idea of survival and learning being equally fundamental and in a strong feedback loop, it begins to make much more sense. Now, I say that in 3 minutes, and I know that it was difficult to understand, but maybe I'll put something in writing.
Yeah,
in the Telegram chat.
I think, Julia, this is the topic for a separate discussion, so we don't want to mix the error of time here. But yeah, so let's move on to the maybe next question right here. Thanks.
Okay, I'll have to say goodbye.
Okay,
and I hope to see you in one of the next meetings.
Yeah.
Bye.
Okay, so the next thanks, bye. So the next question: is it possible that the most fundamental laws are those related to evolution and natural selection? So here we kind of already discussed it. It seems no. At least in this framework, the fundamental laws are not evolution, are not natural selection, but the learning. Now, but the evolution and natural selection is something that emerge from that on the higher levels. So let me, if there are any questions with that, because we kind of discussed it already, we can shift up. Okay, the next one is, given what we know about physical laws, evolution, natural selection, couldn't we describe a tree of life as being inevitable in a universe this size? Well, I mean, it's a harder question, because here we would need to discuss not only how individuals, individual organisms evolved, but how the entire biosphere evolved, and that produced lots of different variants of organisms, and how they all collaborate together. And so I think it would mean, all it means that the universe underwent many phase transition, those biological phase transition, where new levels of complexity were formed. And the newer complexity you form, all of a sudden, all of the lower complexities, all of the lower levels become kind of less important. So you create this, biosphere, and now you can sacrifice individual organisms, even if they die out. That's okay, because for the this is like programmed death, but on the higher level, it's okay if it is good for the entire biosphere, the overall objective on this highest level. And then again, at this highest level, maybe you can still be puzzled by learning versus survival, which one is more fundamental. But on the lower levels, seems to be that the learning is beneficial rather than survival. Okay, well, we're coming back to the same questions. I want to get to other comments. We did spend a lot of time on the first question. So the next one, how did life evolve into complex organisms we see today? And that's again, we kind of discussed, the phase transition. After a phase transition, first, cells formed, the cells decided it's useful to collaborate, assign different roles, then the groups of organisms and the higher levels were forming. Now, the reason why all this complexity had to be created is because we wanted to create the system that is adaptive, right, to changes. And so if all of a sudden you see organisms that cannot adapt to changes, then it dies. Dinosaurs, right? So they were very good in surviving up to recent past, and then all of a sudden some sudden change to the environment took place, and they were not able to adapt to this quickly enough. Now, there is actually a very interesting concept in the machine learning that describes exactly that. That's called overfitting. So you have some data, you learn them, and then you kind of learn them very, very well. And then the data change a little bit, and that's it. You're not able to follow them. Your loss function becomes huge. You die. And that's one way of viewing why dinosaurs died is just they overfitted. They were very good in living in the environment that they lived in, but the sudden change, they were not able to adapt. They were it was too sudden for them. They because of the overfitting, because they learned something very well, they were not able to predict and survive in this new environment. Okay, any other comments?
Is another way of thinking about that is that they found a local minima, and
yeah, that local minima was pretty good for whatever events happened to them like a million years before they died, but then sudden change took place to the environment. There was not enough food, the temperature fluctuations, and they were just not able to adapt to that quickly enough, and so they had to die. And that's kind of the overfitting. At some point we'll discuss it, but I also have a hypothesis that's is also created to aging, where aging is basically you are overfitting. You are kind of pretty good in predicting whatever the environment is, but you reduce the complexity of the environments. You keep reducing it. You exercise less. You do the same type of work, and then you do even less variance in your behaviors, and that all overfitting. And then all of a sudden you are in this very good minima, but then if something else comes around and you suddenly need to get up fast, then you experience pain in your back just because you thought you were still able to do that, but that's no longer the case. You were a pretty good sitter, you were a very local minimum once you were sitting. But okay, we'll discuss those things as a medicine comes around, because I think that those are fun to discuss. But other comments or questions on biology?
I've got maybe addition postscriptum to the opposition between learning and survival. Mm-hmm. Actually, there is no opposition learning survival. There is an opposition of learning and stability. So if an organism learns something for survival, it may be better, optimal in many cases to stay with what it learned. While learning means changing, and sometimes the results of changing are unpredictable. Mm-hmm. Maybe I'm wrong, but I think that from the point of view of learning dynamics and neural networks, some algorithms are it's stochastic learning. So mm-hmm. you change something, but you don't know whether it will be for good or for bad. Mm-hmm.
Yeah. So when I say
loss function, so some change maybe may lead you to some catastrophic results from the point of view of survival. So maybe this is the link between learning and survival through stability.
No, but what's the objective? Is to still learn, or so let me just. I think you raised a very good point, and again, I need to get a little bit into mathematics here, but I will. So when you're saying that a system is learning, but it's still changing, what you are saying is that there is a quantity that is related to temperature in physics. Basically meaning you're going to some minima, but you are still fluctuate a little bit about it, trying to find even better minimum, right? And so what happens with overfitting is that you get stuck in the local minima and you decrease those fluctuations too much, and you are not able to acquire the even better and true minima, and you get stuck, and that's kind of overfitting your. And so the natural tendency of the learning system would be to increase these fluctuations and to actually explore other minima. And yes, some of them will be bad, and you know, you will die, but you know, you've tried, right? The other organisms will try it again, and then you'll find an even better minima. So, but then there is always this balance between trying out new directions or staying where you are because you know it's kind of okay. And my point is both dinosaurs and aging is the same problem, where you say, well, I'm pretty comfortable here, I'll just stay in this local minima, but that's not the right answer because the environment keeps changing. And so if you do not adjust it, or you just stop you know, learning how to adjust to the environment, and it's constantly changing, it's like it changes during our lifetime. Of course it changed over millions of years. And if you decrease the temperature too much, you get stuck there, and then you are guaranteed to die eventually. Now, the solution for that is to keep up your temperature. We'll talk about that more. It's a fun topic to connect.
So I think that maybe we can formulate it as managing a risk of changing that can be in favor of better learning, or
yeah, there's a balance. Katja, you're absolutely right. There's a balance, and and this balance is like on all scales. I mean, think about you know, businesses or politics, right? So do you want to freeze your system and like don't change any laws and like keep where it was?
Yeah, exactly.
Or do you want to like explore possibilities? And if you keep it frozen, if you don't change anything, now the system will be in a good minima, but then sudden change in the environment comes in, and
it loses the ability to learn.
Yeah, to adapt, right? And I think this is like a problem with all living systems, and that, you know, aging has to do with that, and you know, the same comes with businesses, with politics, and so we'll have fun time discussing it for sure. Yes.
Since we're on, this is a great topic. Since we're starting to move towards philosophy, I think if you actually look at the way that humans evolved, it seems that we evolved two personalities in our societies. A personality that's conservative in its viewpoints, where it wants to keep things the same and kind of stick with the past and stick with what works. And then on the other spectrum, there's another type of personality, which is the explorer. He goes out in the world, he's always trying something new. And it seems that's sort of what evolution decided was a good mix of, like, might get themselves killed or might find a new source of food, might survive a long time. So I feel like that type of duality stretches all across the learning systems and really fascinates me.
Okay, Josh, I think you're explaining genders now. You know, women are staying home. You know, well, not now, but you know, for thousands of years, they don't like changes. They want to have a safe environment. This is all good, and men like try to run around and, you know, hunt and explore possibilities. Now, of course, now it's you know, it's all changing, and then there is more of a mixture, you know, of different personalities that are not dependent on gender. But I absolutely agree. This is everywhere. This is on all levels, and thermodynamically. And I will be advertising it to explain it thermodynamically. One is called the loss function, average loss function that you're trying to minimize, and the other one called the entropy. So and then the really the balance between the two is called the free energy. So then that's the one that you're saying, okay, yes, some people are more entropic, they're trying to, explore options, like younger people, for example, right? And that's more psychological questions now, but younger people are like trying to actually explore more options. And so in their behavior, entropy dominates. And then they're never happy with what was before. They're, you old folks, you did it all wrong. We know how to do it better, right? And all the ones, like, we all tried that, didn't work. We already cooled down. Our temperature is very low, and so we're really happy with it. But the truth is that is in the middle. You should nor be conservative in a political system. You should nor be conservative, nor liberal. You should be in between. You should know how to adjust, minimize the loss, and how to maximize the entropy. That's what I call the second law of politics. Right, so the combination of the two, that's important.
Yeah,
Alex, say something. Go ahead, Alex.
Thank you. Well, again, meine Damen und Herren, sozusagen, ladies and gentlemen, the point is that we need to define things. I mean, now we talk about learning. What is learning? And we talk about learning as changing. Not every learning is changing. Sometimes learning is conservative, is directed at preserving status quo rather than changing it. And survival, exactly the same thing. We talk about survival and we talk about existence. What is existence? Existence is static. Survival is more dynamic, but is it reactive or proactive? We need to define that too. So before we go into this,
Alex, I love your approach to defining everything. I really love it, but
I'm German, I can't.
But learning is not changing. This is wrong definition. Learning is not changing. Changing is just dynamics. The word dynamics is changing, and there are different types of dynamics. And there is the learning dynamics, and there is the one that I call activation dynamics. And the difference between these two dynamics, it's not like everything learning, no. So there are some dynamics which are learning, and they lead to the minimization of entropy. So it's entropy destruction. You're trying to make make a model of the environment which is more predictable, right? You make sense. And the other one is other way around. Entropy grows through the activation. So please do not equate changes with learning.
No, I'm happy to accept your definition. The point is that I'm not aware of it. And
so the right definition is the following. So you have all of the degrees of freedom, variables. Think about that. And then those variables, some of them you will be able to adjust and learn, and others you don't. So they're trainable and non-trainable. And learning is you take all those variables and form a function out of them. It's called the loss function. And learning is the dynamics that tries to minimize it. Now, what is that loss function? Like, can I write it down? That is a difficult question, and that's kind of what all the research in the neural physics would come down to. You write down a loss function and see here's the dynamics of particles that resemble electrons or something else. Now, once you move to one layer up to biology, cells, what is the loss function there? Can we write down a function that describes loss function? And there it is closely related to the logarithm of the fitness function. And then in each level, you should be able to write down this function. But it's always, learning is an attempt to minimize some function. Okay.
Well, this is a completely new vocabulary for me. I mean, my vocabulary is completely different. Now related to electrons and so on. But I'm totally lost here.
No, but forget about electrons. But like a theory of learning, it is you have some objective function. We call it a loss function. Without it, there is no learning. If you didn't write a loss function, you're out of business. This is not learning theory. Okay? There's no learning. So there has to be an objective function. There has to be this loss function that you write down. And then your dynamics is to minimize it. Okay, so that's kind of like takes us back to the first questions of the first meeting. But yes, it is. This is essential. Learning is not just changing. No, everything is changing, but not everything is learning.
Vitaly, maybe learning is attempt to find an attractor for dynamical system. Maybe
I can explain in a dynamical system context, Alec, for you. That's again, I mean, I cannot use terminology that everybody will understand, but from the dynamic system of view, yes, it is the direction in which Lyapunov exponents are negative, and the trajectories kind of contract, and like you start with a small perturbation and it dies out. Yes, in the context, but the learning dynamics of neural network has a precise mathematics that comes. The reason, like, why I'm excited about actually applying the theory to other branches is because we have mathematics. Right? Without mathematics, it's just words. Okay, you know, one person means by learning one thing, the other means the other thing, but we have a particular definition of what it is. Okay, and that's why we should you know stick with it, learn it, and work with it. Unless we come up with the other definition, and like you know, maybe we can come up with a generalized learning idea. But okay, so now it's your turf. We're stepping on your turf, Alex. It's philosophical implication. And I know you're going to say define this, define that, but nevertheless, I'll read the question. Okay, let me read the question and see if we start with the defining everything from scratch, we're not going to make progress, but at least we'll try. So first philosophical question. It's in the philosophical implication. I don't even know if I can answer it, but I can read it certainly. What is the nature of reality and how can we know it? Do we live in a simulation or a neural network? So it seems like the nature of reality is the question the philosophers would always, you know, talk about. Now, for me, all it means that what is the mathematical model of explaining the observational data, and then I can look at the two proposals. One, let's say it's a simulation, and the other it's a neural network, and I can compare that, you know, head to head to see which one wins. But maybe others have other notion of what the nature of reality means.
Well, in any case, reality is always a form of consensus. So it's a convention. Our understanding of reality, and it's extremely deep question because there is a question of also our understanding of reality and reality itself. How do those two things coincide?
Right, and for me as a scientist, there's just one question: understanding the reality, right? So for me, and it comes back to this duality, right? So if I have a mathematical framework that can explain all of the observational data, that's it. I've done the best I could with this. Right? I don't need to say what the reality really is. I can just say, well, here it is. Here is my model that best explains in the best way the universe. And from that perspective, I can answer simulation is not in a good shape because simulation, you know, you really need to code it. Will come with bugs. There will be a lot of useless stuff that you would need to simulate. Let's say you're simulating the standard model. It will not be something that you will easily recreate. But neural network, you just set the rules and let it go. I mean, there is no need for you to fine tune, to debug your code, right? We live in a simulation. It will just work on itself. So in this case, I would say that it probably is a closer resembles the neural network dynamics. Also, the people who try to describe it through simulations and through cellular automata, there are problems there. And the biggest problem again comes, in my opinion, from this inability to identify. There must be some learning degrees of freedom because the entropy doesn't completely go, but you really identify and separate the two types of degrees of freedom: the learning and the training, and trainable and non-trainable is absent there. But again, that's philosophical, so there's no right answer here, right?
I envy your simplicity of your world.
The simplicity of the fundamental laws. Yeah.
An elegance of it, if you like.
But that's kind of the whole idea, the whole hope, right? Even physicists that are working on the standard model, their hope is that you write down some simple Lagrangian and everything else is emergent from that. So that's kind of all other phenomena as just come, but you have to show that they come. You cannot just say, your system has to be complex enough So simple harmonic oscillator, for example, is not going to describe the universe we live in, but more complex system, presumably. Okay.
Can
Here
I
we go.
put?
Yeah, go ahead, Alex.
Yeah. Can I put a bit more simplicity? And this man
Even
who
more.
did it, will be very well hated. So I wouldn't tell you who is he. Okay, I'll send you like video later. But he is saying there is only one field which is undivided. There is only one field which is undivided. Okay. So and this man, we have to hate him. Okay. So and I'll be sending this thing. So Alex will hate him.
No, I mean I think we come here to another proposal, is that comes razor, right? Principle, another principle. Should we complicate things beyond to what's needed to explain what we have, what we see, what we
or experience? I
don't think we should. So now I will be happy to complicate things when I see that there's something doesn't quite, work. Then you need to adjust it. But until then, we shouldn't do that. Actually, this was another. I mean, since we have this topic of criticizing philosophers, let me throw one more stone or rock in their direction. It is true that physicist mindset is you start with something very simple as possible, and then try to see complex things emerge from it. Okay, so and then philosophers say, well, no, look, the universe is complex, and let's not forget this and that and that and that, and then maybe we can some kind of make sense of this. So this is another level of thinking. Physicists would always start with the simplest and work yourself to the complex behavior later. Now, unfortunately, we get stuck at chemistry and then never made it to the biology levels, but that was the hope that eventually we can make it all the way. So here the program is suggesting that maybe we can make it a little bit further. I'm not sure we can make it all the way to philosophy, but at least biology, psychology, and computing.
But let me just say one thing in defense of philosophy. I think what I hear constantly from you, is that there's some sort of you're patronizing, all those philosophers, they make things unnecessarily complex. I have to tell you, I don't know whether I'm sure you had a chance to read some of the philosophical treatises. Philosophy is indeed a science, and it has a tremendously rich vocabulary. It has a tremendously diverse and very dynamic, indeed, apparatus with which it operates. And it has a tremendous variety of instruments, methodologies, and ways of analyzing, describing different phenomena, and trying to understand it and simulate it, emulate it, replicate it, and so on. It's a science par excellence. So I would like to first and foremost to warn you against constant references to philosophers as some sort of a dreamers who sit there and scratch their heads and try to come up with yet another parable. That's not the case.
No, I think you misheard me. I think it's the other way around. I think we're all philosophers.
No, and that is another mistake which you make, because it will be the same as I would say, well, we're all mathematicians. 2 plus 2 is 4. That is the end of my mathematical understanding.
Right.
But you are not a philosopher, my dear. You are very practical. Yes. No, I would deny you that. It's a terrible mistake to make.
So let me just finish the sentence. We're all philosophers. We have different toolboxes. This is the only difference.
No, not at all.
So if we all agree.
Okay, then I'm a physicist for you. All right? I just have a different toolbox.
Exactly.
2 apples.
Yes.
And two oranges. That's all my toolbox.
That's great. But we if we had the same toolbox, we wouldn't be disagreeing. Like in physics, for example, we never disagree if we start with the same assumptions, do the same calculations. We never disagree. There is no disagreement. The disagreements only come if we have different assumptions, if we do different calculations. We are like.
That's why I insist on terminology, which you actually ridicule. You say, well, whatever, Alex.
No. I'm with you on the terminology, but I think we already discussed that even what is the learning apparently was not understood. Learning is minimizing a loss function. Okay, now
But that's not how you describe it in philosophy. That's a completely different. Or you should say, well, this is how it is, and I would accept it clearly.
this is how it is. This is how it is.
Okay, fine.
Okay,
Good.
now
then I know which universe
whatever it is in philosophy,
which universe you inhabit.
okay, whatever it is in philosophy, we should learn and map it. Remember, we talked about mapping.
Absolutely.
Yeah. So we should understand what is it means in philosophy and try to understand why is it not a minimization of some function due to the learning time. Where was the bug? What happened? Why did the same word that in both cases should represent the minimization of some loss function became corrupt, broken? Because this shouldn't be. It should all be meaning the same thing. And then okay, so now
it's $1 million question. Why doesn't it?
No, I'm telling you why. So in my understanding, okay, I don't think we'll have time to go all philosophy. My idea, the reason why that happened is because those branches diverge from one another. Okay, the philosophers are not communicating with physicists. Physicists are not communicating with biologists. Biologists are not communicating with psychologists, and it's all became disconnected fields. And
you have extremely specialized language you develop, because I'm surviving for an hour and a half through the discussion,
right,
of which I understand maybe 5% because I speak English, but right, that's about it.
Right, I understand. Yeah. So, but the idea is to unite, right? So, anyway, again, this problem.
To agree first on certain definitions and then move forward. Yes.
I think it's impossible to agree without the toolbox. It comes first.
I bring my oranges.
Yeah. So we need a toolbox. With the toolbox, we can agree on certain things, and then we can move forward. Okay. All right. Perfect. So let me read the second question, in which if we argued so much on the first one, the second one is impossible. And I'll probably just say it that at some point we should discuss it, but we will not have time to discuss. What is the meaning and purpose of life, and how should we live our lives? So,
what is the meaning of meaning? Let's start with this.
Okay. Well.
And then
No, but you understand that these questions can ask about what is a question, and then you will never make a progress. Okay. So what is the purpose of life, and how should we live our lives? Again, learning theory tells you very simple. The purpose of life is to learn. Okay, the more you learn about the environment, about the universe you live in, the more you satisfy your life. How should we live it? By learning, right? So now, is this the right approach? I don't know. Maybe not. But at least this is how the theory tells you that you should live. Okay, so I think this was a very long discussion, so we didn't have time to go through everything. We should probably make a cutoff to the meetings, and I think 1 hour and a half is more than enough, because after 1.5 we just our brains stop functioning, right? Now the thoughts becoming too entropic, and then we need to cool down at some point. So let's next time we'll probably only stay for 1.5 hours, but we'll see if how many people will show up next time and how this will go. Anyways, guys, thank you so much for coming, and